Hello gentlemen, welcome to my channel. In mathematics, the whole work is about the calculations, and the calculations done are for the major calculations. If we go for the minor quantities, we will see whether the same formula for the calculation of for the major quantities is applicable for the calculation of the minor quantities. The alternative way of calculation done for the minor quantities adopted. The correct or the proper way of doing the calculations for the minor quantities or for the minor differences in the quantities. The calculations may be for the relationship between the two cases where one is dependent on the other. It is seen in general that in algebra, when we have two variables like for y being equal to a coefficient multiplied by another variable, that is x, we can write this way that y is equal to ax, where a is a non-zero number. It can be such that y is the cost of total items being bought, which is dependent on the price of each item's amount of the quantities being bought. In the cylinder, as the height increases, the volume also increases in the same proportion. But when the radius changes, the volume would not change by the same proportion, but according to the square of the change of the radius. There are two kinds of changes. One is directly proportional to the change in the variable, and other one is according to the square of change of variable, just like the changes in area. So the pattern of changes is not always a direct function of the index of 1. It can be even index of 2 to the variable. The changes have to be derived. We have to take the very small gaps over which the change is taking place, and from that we can have an idea about how the functions change. The change in the function divided by the change in the variable gives a new name, that is the differential. Rate of change of the function according to the change of the variable is called the differential. Means the way it gets differentiated from its previous value is called the differential. Change in the variable should be very small. Otherwise, for the function given by the second order equation, when the variable changes by a certain amount, change of the function would be very high, because the change would be according to the square of the change in the variable. So as the index of the equation goes higher and higher, the changes in the function will also increase according to the index being increased. So that is why we take the small changes of the function according to a very small change in the variable. So today we will see the changing patterns of the functions which depend on the first order equation. Let's take the first order equation as the function y, where a is a real number but not equal to 0. X is the variable. So let's take two values of x. Say x1 is 5 and x2 is 9. So y1 is a x1. Let's say a is 2 and x1 is 5, that is equal to 10. And y2 is 2 into 9, that is 18. And delta y is change in y, that is equal to y2 minus y1, that is 18 minus 10, 8. And the change in x is equal to x2 minus x1, that is 9 minus 5, that is equal to 4. The change in y per unit change of x is equal to delta y by delta x is equal to 8 by 4. That is 2. Let's take another span between other two values of x. Let x3 is equal to 12 and x4 is equal to 16. So y3 is equal to a x3, that is equal to, that is 24. Y4 is a x4, that is equal to 32. So delta y is 32 minus 24 and delta x 4. Delta y by delta x is equal to 8 divided by 4, that is 8 by 4 is 2. So again the delta y by delta x is 2 as it was found earlier. So for the linear equation, the rate of change of y with respect to x is constant. Gentlemen, we have seen how the differences in the function takes place when we take the values of the variable over a large span, and this will be constant for any amount of the span that we take, and it is constant for a function no matter what amount of the span is taken or where we take the value of the variable from which we take some span. So this is about the first order equation, and in the next video we'll be seeing the how the differences and the function behaves when we take the spans or the large gaps when it is applied to the second order equation. So this is all about this video. See you soon in the next video, and I hope it's going to be a real interesting one. Don't miss the next video because it's going to be on the second order equation, in which will be included a special formula for the second order equation when the differences are seen between the small and the large gaps, and we also derive the equation as we have derived in the first order equation for the gaps and the rate of change of the functions. So that's all in this video, and see you soon in the next video. Bye bye.